So just a reminder, so what we considered last lesson was so-called stone instability. So we started again out from a model of freely moving electrons with an interaction potential. Now the interaction we considered was short range, and taking into account then making the extreme limit of short range interaction, we have an on-site interaction, and then taking into account Pauli principle, we see that we can have only an interaction between opposite spin directions. So we considered this model, and then, which is like, let's say, the same universality class as the model we considered before, like for the interacting electrons, only taking into account the screening. And then considered, like in the previous case where we considered the weakly interacting electron gas, we concentrated on the charge channel to derive an effective theory in terms of let's say, dressed photon fields, which take like the interaction between electrons, like observing that the interaction between electrons gets screened. And here now we concentrated, instead of on the charge, on the spin channel, and we considered one specific correlation function, 4-point correlation function, which was like, let's make a spin flip at some point, space point, and then look at the reaction at a different space point, and the space points far separated, so in the large wavelength limit, we saw that this transverse susceptibility build up an instability at a critical interaction strength, which then tells us that something interesting is going on. So there is spin correlations building up, some kind of magnetism building up in the system, and this is now what we want to investigate, like systematically using the field theory approach. Okay, so that was the idea. So this was like the standard thing that we do. Let's do perturbation theory around the non-interacting reference point and see what happens. And there, this instability now tells us that something interesting is going on. And in the field theory, we should probably find some non-trivial saddle point. So let's look at field theory. An effective field theory for metallic magnetism. So we have the freely moving electrons, not localized electrons, but freely moving electrons in a metallic system where some kind of magnetic order seems to build up. Okay. And now we just do what we did before, so we follow our 5-step program to build up an effective theory. So just exactly the same steps as in the previous example. So the first step, we always said, is identifying a physically relevant channel, and this is now building on our intuition that we gained from the diagrammatic perturbation theory. So let's just rewrite the interaction Hamiltonian in a different way. So the interaction part is the one between spin up and spin down electrons. So this is the density operator that we defined, no? And let's just rewrite this in a different form. Just make some trivial substitution here. Write this term in the following way. Just write as a sum of spin up and spin down, and then as the difference of spin up and spin down squared. This is the same as this contribution here. Now we did this separation because this would be what is just the total density. Okay, density, spin up, spin down. The difference here is just the z component of the spin. Okay, so we can write this as u force sum over I is here the discrete lattice, and then we have here n I squared minus I minus Okay, so this means that if we now translate this operator into the interaction term in the action, we change well, the operators for the eigenvalues, the Grassmann variables, and then get from the construction of the field integral also some time dependence, imaginary time dependence. So this gives rise to the following. Where now these operators are expressed in terms of the Grassmann variables. No? So this would be psi bar, and I here is sum over sigma, psi bar, I sigma, psi I sigma, and SID is sum over sigma, psi bar I sigma. Now comes the sigma Z Pauli matrix, which is diagonal, so I sum here over the identical sigma. Okay, just to recall density. Okay, so this is just a trivial reformulation. Now, why do we do this? Because now we have separated from this interaction term the charge and the spin contribution. Okay, let me just make one observation. What we did here was single out a certain basis for the Z, for the quantization axis of the spin. No? So this model already singled out a certain direction in space, saying let's consider spin components in the given direction Z and call them spin up and spin down. Now, if we consider more generally, if we consider local interaction, where we don't single out a certain spin component, so let's say where we have h of u, just very general. We can always rewrite this in the following form: with force I, and then we have I minus SI. Now taking into account the full scalar product between Sx, Sy, and Sc. Okay, so this, I mean, you can just, if you like, you can just check. Okay, what we did here is, for convenience, we already singled out some quantization. Okay. Maybe I should just give here one hint. You can use that. You can write such a term. First, you can write it, symmetrize it like putting this ones here, that you already get like two close to each other, which would be the density. So changing this here, and then you can put this one here with a negative sign. Okay, and then the combinations of sigma and sigma prime, like if you take here the sum over sigma and sigma prime, you can actually write this one half. C plus is minus, plus is minus, is plus. Which is then here just giving the density, and this here is the spin operator. So this is just generalizing what was done here by, well, taking into account, if you take something like let's say if you push this here, and then you have sigma, sigma prime, C dagger sigma, C sigma prime, C dagger sigma prime, C sigma, you can express this as some combination of this. You can just go through it if you like. Okay, so you can always write this interaction as a contribution which comes from the density and which comes from the spin. Okay? Purely density term and the spin term, and the spin term well, is coming from the exchange channel. Okay? It's just like going through the algebra. Now, this is just a comment here that, well, if you make this separation into charge, into density and spin contribution, what we did so far, we considered the density contribution. No? And the weakly attacking electron gas, we made an Hubbard-Satonovich decoupling in the density part, and saw that this, like in the effective theory, then takes into account the screening, which is related to the charge of the interaction. Now what we want to do here is concentrate on the second contribution, on the spin contribution. Okay? And this is coming from the exchange term. Okay? So we have already discussed previously the density channel. And now are going to consider spin correlations induced by the exchange term which motivates us now, instead of looking at the entire interaction, say this is the first contribution, we could also include by decoupling in a different Hubbard-Satonovich field and so on. But now let's only concentrate on the spin channel, okay? So let's just consider interaction only due to spin correlations. Now we have here the minus, and let me just write this down once explicitly. Minus 1 over 4 tau, sum over I, sum over sigma sigma prime, R I sigma, so I just wrote down here once explicitly the spin operator, which is written in the Z component in terms of the gamma variables. No? Okay, so this is just the third Pauli matrix, which is diagonal. So sigma IZ is C bar I sigma, then the third Pauli matrix, the diagonal component sigma sigma, and the C I sigma. Can you read? Yeah. Okay, so what we do here is we neglect the density part. And this is just motivated now. We already considered the density part. There's one interesting thing, which is all the screening going on. We took it already into account by looking at a short wave interaction. There's also can be some spin, some charge density waves building up. In principle, we could consider both channels by introducing another. So what we will do is now we will consider this interaction here and introduce a Hubbard-Satonovich field to decouple the spin. We could, in principle, introduce a second field to decouple also the charge, but this would be beyond what we are interested in here, because from our diagrammatic analysis, we saw that something interesting is building up in the spin correlation function. Okay, and this is the motivation now to say, well, if we want to just like have a description of what is going on there, like in terms of magnetism, it should be enough to concentrate on this. Okay, so again, this is where physics and mathematics go different ways. So this is all motivated by physics. This is like always the first step. Look at the physically relevant channel. It should be all contained in this term. Okay. Okay. I mean, is this readable or? Yeah. Okay. So what we now do is we do a decoupling, Hubbard-Satonovich decoupling in this spin here. So this will be our decoupling channel. Okay. That's the first part. Physically relevant channel. Motivated by our diagrammatics. That's what we are considering. So now comes step 2, which is the decoupling via the Hubbard-Satonovich transformation. So what we do is we introduce a field that will then be shifted to decouple the spin-spin interaction. Okay, so we introduce, as we did previously, some unit operator in terms of some field integral, which is now field which is called Mi, so this is for n. Which is our Satonovich field, which depends on the side index I and imaginary time t, tau. Okay? This is just again normalization is all absorbed into the measure. And what we do now is, well, again, there's some freedom how to do it. You can define it also with a u here. So I just define it in this way because this will then give rise to the simplest coupling between the Hubbard-Satonovich field and the microscopic field here. So let me just maybe write here once more. Sigma I Z is sigma Z. Sigma, this is diagonal. Of the diagonal components. This is the definition of the component. So what we now do is we want to shift this such that e to the minus s in then becomes decoupled. So we do is we shift mi tau minus we have si tau. So the u is defined here. Now if we insert this here, we already see that there will be 3 terms. So one is just identical to that. Then there's a mixed term, mi siz, and then there will be the siz squared, which now comes with u squared over 4. One u just cancels out, so that we have u over 4 siz squared, okay? which comes with an overall minus, and e to the minus s interaction comes with a plus, so they are exactly cancelling. Okay, so once we do the shift, we multiply the partition function we started out from in terms of the electrons with this function. We will only have the mi squared and mixed term from mi and siz. Okay, so writing now 1 times the field integral over the electrons where the field integral over electrons has a non-intact and quadratic part, and then the interaction part, which is this. This then becomes an integral over dm and an integral over c bar c, and some effective or some interaction which now depends on c bar c and m and has the following form. So we have the quadratic term 1 over u d tau, so 1 mi squared mi tau. This is just copying this term here, which I mean still is there after the shift. And then there is the contribution from the electrons, where we have what? The contribution from the electrons has the non-intending part, which is quadratic, and now we have, we have decoupled this term here. That's not anymore there, the quadratic term, but then there's a linear term of the SiZ coupling to Mi. The SiZ is C bar I sigma, Ci sigma, so it's diagonal in spin and diagonal in space, and this is added to the free electrons part. Okay, so this gives us a quadratic term in the electrons where we have the one without m, and then so just the free part, and then another term where the electron spin z component couples to the m. Okay, let me write down this. So this is this one contribution, and then we have sigma, this is prime. For momentum, sigma. Delta P prime. Okay, so this multiplied with C P sigma is just the free part, just the S0. But now we have, due to the coupling to the spin, another term sigma Z sigma, which is diagonal, times m. And the m, again, if you look at this term here, this here will be local in space. So if you do the Fourier transform, you get a convolution. So this now depends on momentum p prime. Then we have structure momentum space. P prime sigma. Okay, all is diagonal in the spin, and here it's actually independent of spin, and here it's just a sigma z component, so it's a plus for spin up and a minus for spin down. And this MPP prime is now a matrix in momentum space where the P prime element is P minus P prime. Okay, this is always because of the convolution you have for a local term in real space becomes a convolution in momentum space. Okay, so this is an off-diagonal matrix in momentum space where the PP prime element is P minus P prime. So this takes some time to get used to it, but you will see this is always like what is happening. So it's kind of quickly. Okay, so more or less clear. Let's see. So this is what we achieved. We started out from the interacting theory of electrons, introduce the Hubbard-Sartonovich field. We now have a quadratic theory in the Hubbard-Sartonovich field and a quadratic theory in the electrons, where the electron spin Z component now linearly couples to this Hubbard-Sartonovich field. And is this clear? I mean, yeah? Or again, just recall, like the local German real space becomes convolution momentum space, and this you can always understand as some matrix multiplication where you have here a matrix. Okay. So this is was just step 3, which is like purely again like automatically we do it once we have identified the channel we want to make the decoupling in. Now comes step 3, which is let's get rid of the electrons to get an effective theory then in the Hubbard-Sartonovich field. Integrating out fermions. Questions up to here? Or? Okay, so just we have a quadratic theory in the fermions, we can just integrate them out. What we get is a determinant here. Okay? So we can write let's call this here the partition function, that's what we're looking at. We can write the partition function, then there's an integral over dm, determinant minus I omega, that's p minus sigma dm. Just make one more comment, like there's one difference you can, if you recall, when we did the decoupling in the charge channel, the density channel, we found a coupling of the electrons to an imaginary phi field, no? So there was some I always related here. Here it's purely real. And this can be all traced back to the sign here, which is from the exchange term, okay? So in the charge channel, the sign was positive, so to make the Hubbard-Sartonovich decoupling, we had here imaginary I, here this is now real, okay? Alright, so here we now again encounter what we had said before, so if we understand, we should actually understand all this as, let's say, a big matrix which now lives in Matsubara space, in momentum space, and in spin space. Okay, so that this is the tensor product of 3 components. And just for notational convenience, this would be again called the free propagator or the inverse free propagator, and with the M would be the propagator presence of some external field. Okay, so we again have here the functional determinant of the propagator of freely moving electrons here, and here of electrons moving in some field M, which couples to the spin, and this field M is now fluctuating, and fluctuations are weighted by 1 over E. Okay. So just to recall, omega is the diagonal matrix in Matsubara space. R space d epsilon p. We have not specified so far, but it's the diagonal matrix in momentum space due to translation invariance. And then, like usually, the complications arise because this M here is a diagonal matrix in space with imaginary time, so it's an OR space. Okay? So there's not one ideal basis which diagonalizes all of this operator. You have a simple basis that diagonalizes this and a simple basis that diagonalizes this, but the overall is always non-diagonal. Okay, so what we do is, again, we rewrite this using that the determinant, the log of the determinant is a trace of the log to re-exponentiate this, and then we arrive at some expression for the partition function in terms of function integral over now the Hubbard-Sotonovich field, where each field configuration is weighted by some action, which is now given by 1 over u. Now sigma I squared, and then we have minus trace log g all minus m. And let me just recall that this trace here is trace over, so this is spin, tensor Matsubara, tensor momentum space, okay? Okay, so this would be about spin up, spin down, Matsubara, and momentum, or if you like, over spin, imaginary time and real space. Okay? And this here actually could also have written g to the minus 1 of m. Okay, so that's again was all like just applying the general machinery, then without like thinking or anything, just applying what we have done before in this special case. So now comes again like the more physical part, where we have to put in some intuition, which is the fourth step, and which is, so we have derived the representation of the partition function entirely now of this composed field, like composed of two microscopic electron fields. We got rid of the electrons, have an exact representation. Apart from that, we threw away the density part, but the mathematical manipulations, once we threw away the density part, up here were all exact. And now come the approximations, okay? So what we now do is to apply mean field analysis to this action. Okay? That's step 4. Which is the saddle point analysis. And there again we have to put in some assumptions or some physical intuition. So what we do is take the functional derivative of the action and set this to 0. Again, what we can do is we can just do it in real space, or we can do it in momentum space. Let's like kind of taste what you prefer. Sometimes it's easier to do all this in momentum space because like this operator here has a simpler structure, I would say, in momentum space, just given the fact that these two operators are diagonalized in momentum space, in the form momentum space. Now, this then becomes a matrix, but that's easier to handle with them here. I mean, it's a bit off the case. So let's just here consider instead of real space, momentum space. So let's rewrite once everything in momentum space. Okay, it's like two things. Q minus Q minus trace ln G. 1. So Q here is again a 4 vector. Okay, so we can the 4 momentum. We do the real or momentum space. If you do the momentum space, well, we should first see like what first term comes in. So let's do the momentum space, and then the functional derivative minus Q. We get here. I should have commented here. There's a factor n, which is always like the number of lattice sides. Okay, that's from the discrete Fourier transform. And this is a beta, or the 1 over t, which is also due to the Fourier transform. Just factor from the Fourier transform. So now, taking the derivative, we get factor 2 n over tu, n of q. And then we said if we take the function derivative of this, due to the trace, we can just handle the function derivative as the usual derivative. Okay, so we get a minus trace g. And then we have to differentiate the g with respect to m. So we get a sigma z and then sigma z. Delta m minus q of this operator m. And we get another minus due to this here, which makes this into plus. Okay? So this is just using again that we have here the trace, which allows us to use here just a simple derivation. So now we have to think about, again, what is this? So this trace now is the trace of a spin up, spin down, and about 4 momenta. This means the trace here, okay, we have spin up, spin down, and then we have here a matrix product G, P1, P2. This here is a matrix momentum space, so the derivative of n minus q times this matrix is another matrix P2, P1. Okay? And then we have to just recall again, well, we just revise this here once. This would be sigma up or down, P1, P2, G, sigma, P1, P2, sigma V, diagonal, and then we have del Q and P2, P1. Okay? And here we just have to recall again that the P2, P1 component of M is M P2 minus P1. So we take the derivative with respect to M minus Q. This will give us a delta P2 minus P1 should be the same as minus Q. Okay? It's just a delta function. So if we use this, then we get 2n T over U and Q plus sigma, and then let's call the P1P, and then we have G sigma P. This is actually diagonal. No, this is still contagious, so this should have written here the m. Let's write it in. So this is not diagonal. This would be diagonal if m would be equal to 0. So this is GP minus Q sigma, and then we have a sigma z. And all this is equal to 0. Okay, so this is just using P1 minus P2 is equal to P. Did I do it right? It's P1 and P2 is equal to P1 minus Q. Yeah. And I call P1 just P. Okay? So we can write this, okay? So we can write this out in components if we like. 2 So we get, for spin up, we get a plus, and for spin down, we get a minus. So we get a spin up, P minus Q, minus spin down, P minus Q. Is equal to 0. And somehow I prefer to write this in a different way. Plus POM. Just, I mean, rearrange the temperature and the effective length. Okay, so this is the mean field equation. Yeah. This is the mean field equation that we want to solve. And again, there can be solutions which could be breaking the translational invariance in the system. Actually, can happen, which would then lead to so-called spin density waves. But we can here first look out for homogeneous solutions. And this is again like motivated by what we saw from our diagrammatic perturbation theory, is that the transfer susceptibility in the homogeneous limit, in the Q equals to 0 limit, build up this instability. So we want to find this instability. It should be fine to here now concentrate onto the homogeneous solutions. Okay? So we make an ansatz, which is here again motivated by what we have considered so far. So we want to understand this instability which build up in the Q going to 0 limit, and this should be, we should be able to understand from homogeneous mean field solution. Keeping in mind that there can be also other cases that can be interesting, but that's not what we concentrate on at the moment. So let's consider the homogeneous static solution, where M of Q can be written as, let's say, some M bar, and then take the 0 component of the system. And let's see what then happens here. Well, this then is M bar, and here we just get the diagonal operator, okay? And what happens then is that the Green's function, so we write just once more down the Green's function here, G minus 1 minus I omega plus epsilon p minus mu minus sigma dm. What is the plus? How did you define it? Minus. So if M is static, this just corresponds to freely moving electrons in some dispersion epsilon p in some constant field, no? Along the z direction, and what couples to this field is just the spin. Okay? So this becomes very simple then. In this case, let's see how detailed. Okay, maybe I'm too detailed here, but let me just write it once down. So this is minus 10. Then we have the sum over p. Minus M bar to minus M bar. Okay, just the second contribution where this becomes minus. And let's Let's see. How detailed. So what you can do here, you have, so this is just plugging in this ansatz into this equation, no? And then using here the Green's function that becomes simply diagonal momentum and Matsubara space due to the fact that this is a constant. Okay? If this was not constant, you cannot so easily diagonalize it, but here it's simple. So now what we can do is we have the two terms, one with the plus m bar, one with the minus m bar, so we can bring this to a common denominator. So all this itself is proportional to m bar. You know? And then we have the product of this here with the plus m bar and with the minus m bar. Here we have a sum over p and the sum over Matsubara frequencies. So what we can do is we can just do the sum over Matsubara frequencies. Okay? So if we do here the sum over Matsubara frequencies, what we integrate is a function which has two poles. One is minus one at epsilon plus at epsilon p minus mu m bar, and the other pole is at epsilon p minus mu plus m bar. Okay? So if we do brought this to a common denominator, factor m bar cancels out this one here, and then if we do the Matsubara summation, there will be two Fermi distribution functions. One depends on epsilon p minus mu minus m bar, and one on epsilon p minus mu plus m bar. Okay, so you just write down the result after bringing this to a common denominator and doing the Matsubara summation. Okay. Then this becomes no, I think that's I do one intermediate step because otherwise it's getting too much. So what I just write down here, where we convert, so that's one step before, where we convert the Matsubara sum into contour integration. So here, this Fermi distribution. Okay? So passing from here to here, the 2m bar comes from bringing this to a common denominator, and I just rewrote the sum over Matsubaras here as a contour integral. Okay? This is a Fermi distribution function. So now doing here this contour integration, we pick up two poles. One, and I introduced here, I mean as always, CP, like the energy measured from the Fermi level. So now you will pick up two poles. One at D being C plus and minus m bar. Okay? So let me just write down the result after you did pick up the two poles. What you will find is, well, for example, the pole at Z equals Cp minus m bar will give us a dominator 1 over m bar, and then the Fermi distribution function evaluated at this point. And the other one will give us a 1 over minus m bar, so with the opposite side, so 1 over plus m bar, 1 over minus m bar, and then the Fermi distribution function evaluated at Cp with a different sign here. Okay? So what you get, this m cancels out. Actually with a factor 2, that we get n. There's a minus because you pick up the pole in the mathematically negative sense, and you end up with a sum of a momentum minus okay. This is just the result from doing the contour integral and picking up the pole. Okay? So now it's convenient to do like what we always do to convert this momentum sum into an energy integral. And the energy integral, so this conversion is given by introducing the density of states. Okay? So if we introduce the density of states, here density of states per cycle per spin. So we have the 1 over n is defined in the density of states. Defined in the usual way that you sum over delta functions. DOS like density of states per spin and per site. Then you can just convert this sum over P into an integral over energies and the density of states. Okay? So then we find that this is equals to okay. Now, this actually has now a nice interpretation, so we arrive at this expression here should be equal to this expression here. So what we integrate is the density of states times the Fermi distribution function. But this is just counting how many electrons you have. Okay? So this is counting the electrons. Now the m here appears with a plus sign, so the energy was a plus m, which would correspond to the spin down electrons. Okay, so what we count here actually, this here is just the number of electrons with spin down, and this is the number of electrons with spin up. Okay, so if you recall epsilon plus and minus the m bar is nothing but n. So with the plus is spin down and with the up spin up. Then we can rewrite now the homogeneous mean field equation, putting the u half on the other side. We find that m bar equals to u times the sigma z, the expectation value of the sigma z operator, and the expectation value of the sigma z operator corresponds to the difference of spin up and spin down. Also, this is like explicitly written. Epsilon plus. This is the mean field equation. Okay? Questions or? S, para onde S fora? Hã? Não, S2M, na verdade, se eu vou pegar o polo, olha, vai ter um polo quando Z é igual ao CP, aí você vai ter um polo, vai ser 1 sobre 2M bar com a distribution, tá? Esse é do polo aqui. Okay? So, what does this equation tell us? Well, it tells us that we can find a finite mean field value for the Hubbard-Sarton-Rich decoupling field if we have a finite expectation value of spin inside the system. So if there is some magnetism in the system. So you would expect that, well, if you have just, let's say, of course, if you have non-attacking electrons, spin up and spin down, there's no reason why this should vanish. Okay, so what we see is that indeed this Hubbard-Sarton-Rich field M is like an order parameter for some magnetic order. Okay, so if there's no magnetic order, this is 0. However, its interactions lead to some ordering of magnetic type, then this expectation value of the sigma z operator will build up a finite value. And this is reflected in a finite value of the mean field. Also, we see that this can only appear, of course, in presence of two interactions. If interaction is 0, this will always be 0. Okay. So what we see, there might be some finite magnetization due to the interaction, and our Hubbard-Satonovich field in the mean field approximation just accounts for that. So by linking the Hubbard-Satonovich field on the mean field value to an expectation over a finite spin, so this is the order parameter for magnetization. Okay. So this is now different from our previous example, where we can see, actually we should now see if this is possible to have such a finite magnetization, but if so, then we see that indeed there might be solutions to the mean field equation which are non-trivial in the sense of finite quality. So just write down some comments here. So the homogeneous ansatz, aesthetic ansatz, here turns out to be the order parameter for magnetization. And now what we could expect or assume, but again this has to be then in the end, we have to verify if this is really what happens. So what one could expect is that the system will undergo a second order phase transition from non-magnetic to a magnetic phase. So second order phase transition would mean that this m bar continuously builds up from 0 to finite value. So it doesn't jump to some finite value, but if you start at interaction being 0, well then magnetization is 0, and then if it is really a second order phase transition that occurs to the magnetic field, this m will continuously build up finite value as you increase the interaction. Okay? So this is like what we could first expect, like or think. We have to later on verify if this is what happened. But let's assume that there is a second order phase transition to the magnetic phase, and then you can just figure out where is the transition taking place. And this is if we take in this equation the limit where we say m is a finite value but very close to 0. We try to solve this equation, the limit of m going to 0 but still being finite. So let's call this the limit of m going to 0 plus. Okay, so small magnetization. So where this is going to happen, that this becomes a small finite value, this would then mark the second order phase transition point. Okay, so assuming that we have a second order phase transition, we can, by taking in this equation this limit, figure out where is the transition point. Okay? Later on we have to say more about second and first order phase transition. But let's say first, let's expect or assume the second order phase transition. So this would mean that the expectation value for the C component, which is the magnetization field or the Hubbard-Satonovich field, M, because they're just proportional to each other, so whatever we say about this also applies to M. This, the second order phase transition grows continuously from 0 as to some finite value as interaction is increased through some critical value of the interaction strength. You see what denotes the critical value of the interaction strength. Okay, so this let's assume this. Now, if then m of u, magnetization as a function of u is a continuous function, then we can get the second order phase transition temperature, or maybe first can get the second order. Let's first consider the quantum critical point. Can get the quantum critical point, so that would be the phase transition taking place at temperature 0. Some critical interaction strength by sending m to temperature to 0. Okay, so we first can figure out quantum critical point, and then we can also get the second order phase transition temperature. Or the phase transition temperature. And we then go to some very small finite value and keeping interaction fixed. Okay? So based on this idea that, well, there's a second order phase transition building up, we can first look at the phase transition taking place at 0 temperature as a function of the interaction strength. Okay, so taking this limit. But then we can also look at the second order phase transition at finite temperature by keeping the interaction fixed and seeing where we get a finite solution of, where we get a solution with a finite m bar as a function of temperature. Okay? And this is what we are going to do to figure out the mean field phase diagram for this problem. Okay? So, let's see. Okay, maybe just make 5 minutes break and then we go through the 2 points.